Today we're going to take a look at 5.3, which is about logarithmic functions and their graphs. Before we get into what a logarithmic function is, we're going to take a look back at what we did last section and just rehash exponential functions and some of the key characteristics of those graphs. So we're going to graph y equals 2 to the x. When we first talked about being able to graph this thing, we said let's make an xy table for it, and we picked the 5 easiest numbers that we could for our xy table, so -2, -1, 0, 1, and 2, and we plugged those numbers in. When we plugged in the 2, it was 2 to the second power is 4, and then we came up to -2 and we did the exact same thing. Remember, for a negative exponent, 2 to the negative second power, that's the same thing as doing 1 over 2 to the positive second. We're basically taking that base of that 2 and we're going to flip it to where it's not. So we flip it to that denominator, and this should get us then 1/4. 2 to the first would be 2, so 2 to the negative first would be 1 over 2, and then anything to the 0 power is always 1. When we plot those 5 points, we should get a graph that looks like this. This is where as it moves more to the left, we're going to get closer and closer to that x-axis, but we're not going to cross over the x-axis. That's where the horizontal asymptote is, and we want to make a note of just drawing a dotted horizontal line to remind ourselves that we're not going to cross over that x-axis. We're going to label that asymptote. So our domain for this graph, it can go as far to the left, as far to the right as possible, so our domain's all real numbers. Our range, since we do have an asymptote, a horizontal one, and we can't cross over that, we can cover everything that's above that, so it would be y is greater than 0. The intercept that we have, we only cross one axis, the y-axis, so that would be the point 0, 1, and we said the asymptote is the x-axis, the horizontal line. Any horizontal line is always y equals, and then the number. We're going to do the exact same thing now then for the inverse. For the inverse, remember for inverses, all we have to do is switch the x and the y. So all of our y values will become the x values. So the 1/4, the 1/2, all the way down will become the x's, and then the x values are going to become the y's. And we're just going to plot these. So 1/4 -2, 1/2 -1, 1, 0, 2, 1, and 4, 2. And that graph is going to have a similar shape to the exponential one. So we're still going to have an asymptote in there, except this time we are crossing over the x-axis, but we are getting closer and closer to the y-axis. So we get closer and closer to the y-axis, but we're not going to cross it. That means this time we are going to have a vertical asymptote at 0. So we'll get closer and closer to that line, but won't cross over it. And then we're going to do the exact same thing down here. Our domain this time, how far left and right we can go. We can go right as far as we want to here, but we can't again cross over that y-axis. So we're going to have everything greater than 0, but this time it's the x is greater than 0. Our range, we're definitely going down, and this, even though it's going out this way, is going up slowly, so we are going to be able to get all real numbers for this one. Our intercept this time, we have the x-intercept now at 1, 0, and the asymptote is a vertical line, and every vertical line is always x equals, and then we put in that number. The nice thing about this is all of these over here, since we're just talking about finding the inverse, we switch the x and the y, so the range becomes the domain becomes the range. We switch that point, we switch that variable, and we get all of those there. Now we've done this a couple times, but what we haven't dealt a lot with is actually changing then this equation. So if we were to take this equation and we wanted to say what's the inverse of this equation, we switch the x and the y, we get x equals 2 to the y, and we said we can't solve this for y, but what we're trying to find is if we wanted to find y, we're trying to find the exponent, as in 2 to what exponent is going to give us this number that's over here. When we work with it that way, thinking about that exponent being by itself, that's where we're going to get into what a logarithm is. So the inverse of y equals 2 to the x is x equals 2 to the y. But again, if we wanted to get y by itself, we're saying y is going to be that power to which we raise 2 to get x. Again, it's the power to which we raise 2 to get x. If we're not quite sure what that means, if we saw a number over here, like let's say this was a 4, we would be saying 2 to what power is going to give me a 4? 2 to what power is going to give me an x? That's another way that we can think about this thing. 2 to what power? That power is going to be our variable, is going to be our y, is going to then equal whatever we have on the other side. In this case is going to be x. Another way of being able to say that then, instead of saying y equals the power to which we raise 2 to get x, is going to be y equals log base 2 of x. That's what a logarithm is. A logarithm is really just talking about an exponent and looking at the exponent as being the thing that is by itself. Now the way that we say this, we don't want to get in the habit of saying log 2x in there because we don't know what goes here, we don't know what goes there, so we give some verbal cues to talk about what's going to be in this subscript here and then what's going to be in line with that log. The way that we read this is log, and then we have to actually say the word base, 2, and then of x. These two words, super important for when we talk about this, is log base 2 of x. That 2 is a subscript. We'll always have a subscript down here with exception to 2 separate cases for that we'll get into later, but that is going to be a subscript, and then this x here is in line with the logarithm. So a subscript and then back in line with that. The notation for this is very important. We don't want to get into the habit of doing something like this because now we're reading this as log of 2 to the x power in there. So log base 2 as a subscript of x in line with the log. So if we look at question number 2, it says, what would y equals log base 2 of 8 mean? What this means then is, if we follow this up here in the bold, we're saying the power to which we raise 2 to get 8 at this point. Or what we're saying is 2 to what power is 8. So when we read this, we're really saying 2 to what power is 8. For this one here, log base 3 of 81 means 3 to what power is 81. And for the last one, we would be saying 3 to what power is 1/9. Now for all 3 of these, we can go back and we can solve all 3 of these if we want to. What power would we have to raise 2 to get 8, or 2 to what power is 8? Well, we know 2 times 2 times 2 is 8, so 2 to the 3rd power would give us 8. For this one, 3 to what power is 81? That would be 4. And here, 3 to what power is 1/9? We're trying to get a fractional answer for this. Any power that we raise 3 to, 3 to the 1st, to the 2nd, to the 3rd, is going to get bigger and bigger and bigger, isn't going to get us a fractional number. But we know 2 things. Number 1, 3 to the 2nd power is 9. And if we use what we talked about back here with it, if we throw in a negative power, we're going to get a fractional answer. So if we know 3 to the 2nd is 9, 3 to the negative 2nd then should be 1/9 for us. The next thing that we're going to get into then is talking about the definition of a logarithm. We kind of just did this by talking about what that log means. This is just going to be a little bit more of a formal piece for it, as in changing from a logarithm to an exponential. We're going to make one little change for this because oftentimes for books we're going to see a slightly different variable in here. But when we say log base a of x, we're going to change this a to a b, because we're talking about it as a base, so it makes sense to use b there, which if we use b here, we're also going to want to use then b right here for it. So we're saying log base b of x is the same thing as b to the y equals x. That means if we have this in logarithmic form over here, we can rewrite this to look like this, and these 2 statements are equivalent statements. Remember, from what we just did, we would be saying b to what power gives me this, so b to what power gives me that x. And again, we can change back and forth between these 2. There are 2 ways to know this, or to remember this. Number 1 is we memorize that definition right there. It's not a great way to be able to do this, but we are going to do a lot with logarithms of changing from logarithmic to exponential and exponential back. The other option that we have is right here, is the base of the log, so that subscript in here. The base of the log is going to be the base of the exponential in there. So the base of one is the base of the other. So the base literally is the base. I don't care what form it's in, the base is the base. And then the exponent. The exponent is equal to the logarithm. So since the exponent is equal to the log, when we see the exponent, that's what's going to equal then by itself equal that logarithm. So the log is the exponent, or the exponent is, when we say is, we're talking about is equal to that log. So the log is equal to the exponent is equal to the logarithm. If we know those two things, we can place all three numbers in the right location. So in number 5, it says convert each to logarithmic form. So right now it's an exponential form. So this problem right here looks like this setup here. We want to rewrite it then to look like that. So the first thing we always want to identify first is the base. The base in this is that number that's being raised to a power. So we have a 2. So we can say this is going to be log base 2. And then we know that the log is equal to the exponent. So whatever the exponent is, that's what the log has to equal. So we know since the exponent is 4, this has to equal 4. So by default, that number that's over here, what this is equal to, then has to go inside the log. So the 16 has to go inside then the log. So this is saying log base 2 of 16 equals 4. If we want to think about this, let's say we don't know that number from the previous slide. Log base 2 of 16 means 2 to what power is 16? And what number would we have to raise 2 to get 16 would be 4. So that would equal 4, which is what we got when we rewrote it. For number 6, 125 equals 5 to the x. We identify the base first. The base is a 5, so this is going to be log base 5 of, then we know the exponent has to go over here for us. This is going to be the exponent, it has to go over here, so the of has to be then 125. So log base 5 of 125 equals x. Well, this is also saying over here 5 to what power is 125? And that would have to be 3 if we needed that answer. The last one to rewrite this, we identify our base. So there's our base, so log base 2 of then that number on the other side equals our exponent. So log base 2 of 1/8 equals x. To convert it to the other form, it's doing the exact same thing. We identify what is the base. We identify what is the log equal to. That becomes the exponent. Then that number inside the log is what that thing is going to be equal to. So our base is a 4. So it's going to be 4 raised to, remember, the log equals the exponent. So this is our exponent, has to be our exponent, and then equals 64. So we're saying 4 to what power equals 64, either from viewing this as literally 4 to the power equals 64, or this log statement is 4 to what power equals 64. For this second one, we identify our base first, so 6 to the x power equals 1 over 36. And for this last one, we still start off with the base. It doesn't matter that it's a variable, but our base raised to the exponent has to be what the log is equal to. So raised to the third equals 27. And that's how we rewrite something from logarithmic form to exponential form, or vice versa. The last thing that we're going to do for the introductory piece of logarithms is we're going to talk about 2 special bases that we have. The first one, it's not in here, but we are going to talk about the common logarithm, or the common log. The common log is if we write out a log and we intentionally don't write a base in there. So if we were just to say for this, if we read this as the log of 5, we don't have a base in there for it. We just write it as the log of 5. If we have an understood base, it's kind of like when you see an x and you're like, what's the number in front of an x that we don't write out would be a 1, or what's the exponent to an x that we don't write out would be a 1, or if we were to put this thing inside a square root, that base that we have right here, or that root that we have right here that we don't see is a 2, those are all understood numbers. For a log, for our common log, when we don't write that base, the understood base is going to be a 10. So when we just see log of 5, this is really log base 10 of 5. And again, that's only when we don't see a base there for a log, it becomes base 10. The other type of base that we're going to deal with is the same base that we dealt with for exponentials, which was base e for this. Is if we have a base e for this, we called this from the previous section, we called this the natural base. So if we put this base in as a log, we are going to call this the natural log. And the way that we write out a natural log without a base is we're going to use ln as our natural log. And again, anytime that we see a natural log in there, we can do one of two things. We can either write this thing as the natural log base e of x, or if we like to just see log there and not view this as another term for us, we can rewrite this then as log base e of x. So for question 11, it's saying find what is x when x equals the natural log of e to the fifth. So there's no visible base in there. So first thing we probably want to do is let's see that visible base. We can write this as e or x equals natural log base e of e to the fifth, or we could write this as x equals log base e of e to the fifth. And then for either one of these, since they're both logs, we can rewrite this into exponential form. So for either one of these, we want to identify that base first for this. Well, our base is going to be, whichever one we look at, our base is going to be e. So it's e to the log is equal to the exponent. Well, the log equals this, the log equals this, so our exponent has to be that, and then that equals what's inside the log. Well, e to the fifth for both of these is inside the log, so equals e to the fifth. That means x has to be, since this is x to a power equals, or e to a power equals e to the fifth, the only way for these to be equal, since the e's are equal, is if those exponents are equal. So our answer has to be 5. We're going to take this then, and now we're going to talk about being able to graph these. The graphing for these is the exact same as the graphing for everything else. So if we think back to what we did for the exponentials, it was name the parent function, name the transformations, make the table, apply the transformations, there's our new graph to it. This is the exact same thing for us. So when we look at this, y equals 2 log base 3 of x plus 4 minus 1, there's our x plus 4 in a set of parentheses, meaning that 4 has to be some type of horizontal transformation for us. We want to start off with a parent function. Y equals what? Now, if we can't think about what the exponential or what the parent function is for this, we can hop down to transformations and talk about what those numbers mean in terms of transformations, and then everything that we name that's not a transformation has to be in our parent function for it. So the 2 that's out in front, the 2 has to be our vertical stretch by 2. That plus 4, since it's inside with the x, has to be the horizontal transformation for us. So that's going to be a translation, since it is adding 4 to it. Inside is always the opposite, so that has to be left 4. And then the minus 1 has to be then down 1. So if we cut out the 2, the plus 4, and the minus 1, that's going to then be our parent function, is log base 3 of x. And now we want to make a table for log base 3 of x. Normally, we pick numbers for x, -2, -1, 0, 1, 2. Let's see what happens if we do this. We put these numbers here. When we plug this in, we're asking ourselves to find log base 3 of -2. This would be saying 3 to what power is -2? We know if we raise it to a power, we can get whole numbers, we can get fractions in there, but we don't get negatives as an answer. So this doesn't work for us. We can't raise 3 to any power to get a negative answer. So -2 won't work. -1 then won't work. We go to 0. We know 3 to the 0 power is 1. But there's nothing that we can raise 3 to actually get 0. So really, the first 3 numbers for this don't work. That means that this right here is really a bad option to go with of those 5 numbers. What we can do to help ourselves out, if we're not sure what numbers to pick for x, is let's rewrite this thing. Let's take this out of log form as is, and let's rewrite it in exponential form. So our base is our base. 3 to the log equals that exponent. So equals the exponent, and then equals to that last thing is equal to x then. If we look at this one and we want to use -2, -1, 0, 1, 2, when we look at that equation, which variable would be easier to put in -2, -1, 0, 1, 2? We just kind of put those numbers in for x, and we saw 3 to what power gives us negatives doesn't really work too well. So instead of putting those in for x, we're going to do a little bit of a curveball and put them in for y, because we can do 3 to the second power fairly easily and get 9. And then that means we can do 3 to the negative second power. If we know 3 to the second is 9, 3 to the negative second is 1/9, 3 to the first is 3, so this would be 1/3, and then anything to the 0 power is 1, and that gives us our table. That table should look fairly similar to the exponential table, except it's just flipped. The x's and y's are flipped because logs are the inverses of exponentials. If you guys can make a table for the exponential, you can make a table for the log then. It's literally just the flip between the two. And at this point, all we have to do is go through and apply our transformations. There's only one horizontal transformation that we have. It's left 4. So we're going to take all of our x values and we are going to subtract 4 from them. So we should get 5, -1, -3. For the 1/3 minus 4, if we have issues with subtracting fractions, one, I think in a previous section we talked about being able to subtract this using money, thinking about you have a third of a dollar and you owe someone $4, how much do you still owe them? The other option, a little bit more mathematical, is we can just flip it around and do big number minus a smaller number. If you have 4 and you have to subtract a third from it, that should leave you with 3 2/3. But really, since we're subtracting the big number, we need a negative out in front of that. So for 1/9 minus 4 is, if we think about that as 4 minus 1/9, when we subtract that, that should get us 3 8/9. But we should have a negative there in front of that one as well. For the y's, we need a vertical stretch by 2, so we are going to double the y's, and then we are moving down 1, so we subtract 1. So we double it, subtract 1, double it, subtract 1, and these should be the 5 y's that we get. We graph these outside numbers now, and that should give us our log graph. So -3 8/9. So right before -4, we're going down to -5. A little bit beyond that, ever so slightly beyond that, we're going to -3, and then at -3 we're at -1. At -1 we are at 1, and at 5 we are at 3. And that's our graph then. Again, our logarithmic graphs that look like this, we should have a vertical asymptote. We should have a vertical line that we are not allowed to cross. And just by drawing in this graph saying that it should go out this way, and we draw it backwards, we can kind of see where the graph starts to level off at. And where it levels off looks like -4. So -4 is going to be the asymptote for us. There's another way that we can figure out specifically where that asymptote is. We'll talk about that in the next problem. But since this is our asymptote, that means our domain has to be everything beyond that -4, so everything greater than -4. The last problem then that we are going to take a look at is a little bit of a shortcut of being able to graph these. And what this comes down to is knowing the parent function and knowing all the key characteristics of the parent. So when we look at this, it's 1/2 natural log x minus 3 plus 2. If we're not sure again what this parent function is, we can name our transformations, all those extra numbers. So we have a vertical compression this time by 1/2. That x minus 3, again, inside is opposite, so we're going right 3, and then we're going up 2. So if we ignore those 3 pieces in here, then everything else should be our parent function. So y equals the natural log of x, or if we want to see that base in there, log base e of x. Now, the shortcut route to this is, if we know what the parent function is, we know that's a logarithmic graph, we just have to think about what are the characteristics of a log graph. And if we go back to the very beginning, here's all of our characteristics of a log graph. The two important ones being we have an x-intercept at 1 and we have a vertical asymptote at 0. If we know those two things for our parent function, that every parent log function has an intercept at 1, 0 and has an asymptote at x equals 0, we can start off with that to graph this because there's two pieces that we can transform. Now, if we don't remember that, what we want to do with this is we want to go the route of being able to make the table for this thing. We're going to come up to this and we're going to rewrite this in exponential form. So take the base, which is e, raised to the exponent. Remember, the exponent equals the log, so raised to the y, and then equals the x. And we're going to make a table for this and transform that using our table. We need one other point that is on this graph to be able to plug in for this thing. So we can either make a table or one other point off of this, one other point off of this. It may be easier to use this here and say, well, I've used 0 for y already for this thing to get an answer of 1. So maybe I'll use an answer of, or use 1 as a value for y, plug that in. E to the first is just e, or remember e is 2.7, approximately 2.7. And there's our three pieces of information that we are going to then transform. We can make a table for these three if we want to make a table to see what our transformations will look like, the point 1, 0, the point 2.71, and we'll just say x equals 0 as the x value for the asymptote. And now we're just going to transform these using this. Right 3 means we're just going to add 3, compression by a half, vertical compression by a half, and then up 2, there's our y's. So add 3 to all of our x's. 4, 5.7, and what will now be x equals 3 is our vertical asymptote. And then the 1/2 y plus 2, 1/2 times 0 plus 2 is 2, 1/2 times 1 is 1/2 plus 2, so 2.5, and we're going to graph those. So the point 42, the point 5.7, 2.5, so 5.7, 2.5, and then we have x equals 3 as the vertical asymptote. Again, since our vertical asymptote is x equals 0 and is always going to start off as x equals 0, the only thing that can affect that is going to be the horizontal translations that we deal with. So if you know that it's 0, if you know that you're moving left or right, your asymptote is always going to shift left or right however much you are shifting left or right. So if we know what we're doing here, we are going to always know what we are going to do right there for this thing. And then we know we've got to have that same kind of curve that goes like this. It's got to go through these 2 points and continue off this direction. And it's got to hug this vertical line. So it swings down that way. And there's our graph of the natural log. And that's it for 5.3.